Welcome to this video in which we will be talking about partial finite differences, so that by the end of this video you will be able to calculate partial derivatives using finite differences. So far all the derivatives that we've been looking at were for functions that depended only on a single variable. But what do we do if a function f is a function of more than one variable? For example, f would be in this case here a function of the independent variables x and y. Well, in that case we know from calculus that we have to do partial derivatives. And from calculus we know how to do that. If we take the partial derivative of this function that is dependent on x and y with respect to x, at a location x equal to a and y equal to b, what we have to do is we have to take the limit of x going to a, keeping y constant and equal to b. Then we take that difference of f of x comma b minus f of a comma b divided by x minus a, and now x goes towards a, but the y value is always fixed to b. If we want to take the partial derivative with respect to y, it's just the opposite, flipped. We then take the limit of y going to b and we fix x as being equal to a. And then we take that limit y going to b of the ratio f of a and y minus f of a comma b divided by y minus b. So when we want to do this with discrete points, now we not only have to introduce discrete points in one spatial direction here, as it was before in the direction of x, we now have to do this in the direction of two independent variables here, x and y. And we call that set of discrete points then a grid or a mesh. So we have pairs of x and y coordinates, at which location we will know the function value f, and at which locations we would want to calculate the partial derivative. Now let's assume the spacing is constant in each direction. So for example, the spacing in the x direction is h sub x, which is just the distance between any of the neighboring points. And we have similarly the distance in the y direction, which is the difference of y sub j plus 1 minus y sub j. Now, hx and hy can be different, but what we're assuming is that they're constant in each of their directions. And now to do the finite difference version of the calculus version, all we have to do is apply the finite difference formulas as before, keeping either x or y constant, depending on which partial derivative that we're interested in. So for example, using 2-point forward differences and looking at the partial derivative with respect to x at the location xi, yj, since it's the partial derivative with respect to x, we keep y constant equal to yj. So we take the difference of f at xi plus 1 yj minus the function value at xi comma yj divided by the spacing in the x direction, which is hx. And we know that this forward difference is a first order approximation, so the order is order hx. Right, and if we compare this to the definition from calculus, you'll see that in this formula we have kept y constant. And y in this case here is at yj, so the y is here in every one of the two function evaluations equal to yj. We want to do the same thing in the partial derivative for the y direction. We just keep the x value equal to the location where we want to evaluate the partial derivative. In this example it is xi, so we keep x equal to xi, which leaves as a forward difference the formula f at xi yj plus 1 minus f at xi yj divided by hy, and we know that that is a first order approximation. Now, we can do this with any of our finite difference formulas. So here's another example. The second derivative using the 3-point central formula, that was in 1D, it was f at I plus 1 minus 2 fi plus fi minus 1. But now as a partial derivative in 2 dimensions, that would be f at xi plus 1 comma yj minus 2 f at xi yj plus f at xi minus 1 yj divided by hx squared, and this is a second order approximation. And since this is the partial derivative in the x direction, we kept the y value constant equal to the location where we want to evaluate the partial derivative, which in this example is equal to yj. Similarly, if we wanted to calculate the second derivative in the y direction, we would keep the x value constant and otherwise apply the same finite difference formula just in the y direction. So here x is constant equal to xi. And the y varies, so we evaluate f at xi yj plus 1 minus 2 times f at xi yj plus f at xi yj minus 1 divided by hy squared, and again this is a second order approximation. But what about mixed derivatives? So something like this, d2f dx dy. Now, we can write this either as the x partial derivative of the y partial derivative of the function f, or we can flip the order. This would also be equal to the y partial derivative of the function f partial derivative in the x direction. So the strategy now is to just apply the finite difference formulas one after the other. And I want to point out that those finite difference formulas don't have to be the same finite difference formula for each one of the partial derivatives. They can be different finite difference formulas for each one of the partial derivatives. So here's an example. If I want to calculate that mixed partial derivative d2f dx dy, let me first calculate the inner partial derivative df dx. If that's to be evaluated at xi yj, I get this formula from before. Well, if I do second order central, this would be f at xi plus 1 comma yj minus f at xi minus 1 comma yj divided by 2hx. This being a second order approximation, I have an order hx squared term. Let me call this finite difference formula there, this fraction fx, and I know that I evaluate this fx at xi yj. Now, I'm going to apply the outer partial derivative d dy to this fx. And I'm going to use second order central here again. So I'm going to calculate the partial derivative of fx using second order central differences at xi yj. So that would be fx at xi yj plus 1 minus fx at xi yj minus 1 divided by 2hy plus second order terms in hy. So now what is fx evaluated not at xi yj but at xi yj plus 1, so shifted by one index in the y direction? Well, that just means that instead of having y equal to yj, I have y equal to yj plus 1. Right? It's a partial derivative in the x direction where I keep the y values constant, in this case equal to yj plus 1. So that would then be f at xi plus 1 and yj plus 1 minus f at x minus 1, yj plus 1 divided by 2hx. Then I have to subtract fx at xi yj minus 1. So I want to do this fx value at yj minus 1. So let me use the formula, and instead of having yj, I have yj minus 1. So that would then be minus f at xi plus 1, comma yj minus 1, minus f at xi minus 1, comma y at j minus 1 divided by 2hx. And then from the original formula, I have to divide this entire thing by 2hy. So I know that these inner derivatives were second order in hx, and this outer derivative is second order as well in hy. So I have two error terms here, truncation error terms, one second order in hx, one second order in hy. So doing these partial derivatives is just applying one finite difference formula to the inner part and then a potentially different finite difference formula to that outer part and combining the two. So let's do an example. Here there are temperature measurements in degrees Celsius done on a sheet of metal where K is equal to 30 watts per meter degrees Celsius. And we have this table here of the measurement values at these red dots where the measurements were made. And we're tasked to calculate the heat flux Q in the x direction at the location x equal to 0.5, y equal to 0.1, using second order finite differences. So that location x equal to 0.5, y equal to 0.1 is up there in the table. And just as a reminder, the heat flux vector Q is minus K times the gradient of the temperature. Then we're tasked to calculate the heat flux Q in the y direction at that same location. And finally, we're supposed to calculate the x direction gradient of the heat flux in the y direction. So how does the y direction heat flux change in the x direction? And doing all of that with second order. Okay, so let's tackle these problems one by one. And I've copied here onto this as well these second order finite difference formulas that I will need. Let's start with the first part. I need to calculate Q in the x direction at a location ij. So where was that location? Let me just mark it in here. It is right here. So then this here would be my I, this would be my j. So then this column here is I minus 1, this column is I plus 1, this row is j plus 1, j plus 2, and so on. So Qx at ij is equal to, with the definition here of the heat flux vector, the x component of this is minus k times the partial derivative of temperature with respect to x, evaluated at the point ij. So this partial derivative I'm supposed to evaluate using second order, and if I'm right up here and I want to do second order in this x direction here, I have a point available to the right of me and to the left of me, so I can use the second order central difference formula. So then this would be equal to, using second order central differences, well, it's approximately equal to, because my finite difference is an approximation, minus k times t at I plus 1, comma j minus t at I minus 1, comma j divided by 2 delta x. The k is in front of that fraction. Okay, let's substitute in the values. So minus k was 30 watts per meter degree Celsius times Ti plus 1. So I plus 1, that would be the neighboring point here, that's 4 degrees. And then I'm going to subtract from this I minus 1j, which would be 24 degrees. So 4 degrees Celsius minus 24 degrees Celsius. So as a reminder, this is the blue value that I've used. This is the green value. Then I'm going to divide this by the spacing 2 times the spacing. And what's my spacing? And I've called this delta x. I can also call this hx. That is the difference here between adjacent points. So that's 0.6 minus 0.5. 0.6 minus 0.5, which is 0.1, which is the same value between any one of the adjacent x points. So divided by 2.0.1 units are meters. Okay, so 4 minus 24 is negative 20 degrees Celsius. Divided by 0.2 is 100 times negative 30. So that would be plus 3,000 watts per meter squared. All right, so that's my heat flux in the x direction at that location. And it's an approximation, right? Because I will have made a second order error. Next up, I'm supposed to calculate the heat flux in the y direction at the same location ij. So that's minus k times the partial derivative of temperature in the y direction. Now if we look at this here, I won't be able to apply that second order central difference formula, which would take this value here at j plus 1, but it would require a value at j minus 1 up here, which I don't have, right? I'm here at this measurement location, and there's no measurement at I'm down here at that measurement location, right? That's the positive y direction, positive y in this direction in the table. So I'm down here, and there's no neighbor in the j minus 1 direction. So I can't use this central difference formula. But in the lectures before this, we derived formulas that were one-sided that we can use at the boundary. And the one that we will need here is the one that goes into the plus y direction, that uses these 3 points. So here in this table, those would be these values here, this value, and this value. Okay, so let me just write the formula out. So that would be negative k times, I'm going to use this formula up here, so minus 3 times t at I comma j. It's the partial derivative in the y direction, so I keep the x index, the I, the same, plus 4 times t at I comma j plus 1, minus t at I comma j plus 2. Then I have to divide this entire thing by 2 times delta y. And if I look here at the spacing between adjacent points, delta y is equal to 0.1 meters as well. So let's substitute in the values from the table. So this is Tij plus 1. This is, Tij plus 2. This is Tij plus 1, the orange one. And Tij is the yellow value. So that would be equal to minus 30 watts per meter degree Celsius times negative 3 times 15 degrees Celsius plus 4 times 40 degrees Celsius minus 65 degrees Celsius, and the entire thing divided by 2 times 0.1 meters. And if we plug in the values, we'll get that this is negative 7,500 watts per meter squared. All right, now, finally, we are supposed to calculate the x direction gradient, so d dx, of the heat flux in the y direction, so of qy, and do this at ij. Okay. So that's equal to d dx of dt, well, got the minus k, so of minus k times dt dy, and all of this at the location ij. Okay, so now what we'll have to do is go step by step. So let me, go back to this formula here and just apply the d dx to qy. Using, it's in the x direction, I can use second order central formulas. So this would be then approximated as qi at I plus 1 comma j minus qy at I minus 1 comma j. And I'm going to divide this now by 2 times delta x. Okay, so now I need to calculate what is qy. So let me write this. So I need, first of all, I have 1 divided by 2 delta x up front. And now I need to calculate qy at I plus 1 comma j. I plus 1 comma j here, that's this green location. So I need to calculate this term here, which is a y direction derivative, right here at I plus 1 comma j. And I need to do this with second order. And I know I can't go central here in the y direction, so I can't use the same type of finite difference formula. I have to go one-sided like I did before over here. So I have to use this formula, right? But apply it at this location now, I plus 1 comma j instead of I comma j. So that would then be t at I plus 1, minus 3 times t at I plus 1 comma j plus 4 times t at I plus 1 comma j plus 1 minus t at I plus 1 comma j plus 2. Right, and if you look at this, this was the partial derivative qy, right? It's the partial derivative in the y direction. So that means I keep the x index the same. So the x index here is I plus 1. So everywhere here, the x index is the same I plus 1. And I'm going to vary the y index, so the j, according to this formula. And then the entire thing here has to be divided by 2 delta y. And now I need a little bit more space. Should have planned better. So let me just move this over here. Okay, because now I need to calculate this term here, qy at I minus 1j. Well, that one is here at that blue location. So I need to evaluate this here, dt dy, at that blue location. So that would be minus 3ti minus 1j plus 4ti minus 1 comma j plus 1 minus ti minus 1 comma j plus 2, and then divide the entire thing by 2 delta y. All right, so just to reiterate, I have evaluated qi plus 1 comma j, and I've done this, let me just make this here green, right, using these values over here. Let me just go a little bit thicker here, these values, right, to evaluate this term here. That's this entire thing. Okay, and then similarly, I have evaluated qy at I minus 1 using these three values here. That is this finite difference formula. And then we've plugged this into the outer derivative, which is the derivative in the x direction where we use second order central. Okay, so now it's time to just plug in the values from the table. So we have equal to, and the one thing I forgot in here is the minus k, right? And which I can move in front of the differences. So I have minus k is 30 watts per meter degree Celsius divided by 2 times 0.1 meters times minus 3 times Ti plus 1j, that is 4 degrees Celsius, plus 4 times Ti plus 1, j plus 1, that's 40 degrees Celsius, minus Ti plus 1, j plus 1, that is 76 degrees Celsius. And then we divide this entire thing by 2 times 0.1 meters, and then minus negative 3 times Ti minus 1j. Ti minus 1j here, that's the 24 degrees Celsius. So minus 3 times 24 degrees Celsius plus 4 times, now we go in the y direction, right? So the next point would be up here. So plus 4 times 40 degrees Celsius minus 56 degrees Celsius, so 6 here, divided by 2 times 0.1 meters. And then if you plug in all the numbers for this, you'll find that this is negative 30,000 watts per meter squared, meter cubed. That's the second derivative. Okay, so that's how you do these partial derivatives, just applying them one after the other if it is a mixed partial derivative. Thank you for watching.